recording going. Here we go. Okay. So thank you so much for joining us for Superstellar Friday. I'm very excited about our presenter tonight. Dr. Shawna Hollen is an assistant professor at UNH since 2015. And I have to admit that when I learned about her research, what I thought was, I have no idea how that works at all. The idea of a 2D material is, I think, something I really can't comprehend. So I am really looking forward to this opportunity to get a better sense of what that means and how you even do research on something like that. So what I'm going to do is I'm going to turn it over to Dr. Hollen and mute myself, but remember, use the chat, use the Q&A, and we'll get all of your comments and questions over to her. Thank you.
Thank you so much. It's so nice to be here and to talk to all of you about some of the things that I do professionally and for fun. So it's a little bit different for me to talk to an audience I can't see, but I will do my best. I wanted to tell you today about taking pictures of atoms, which is part of what I do in my job at UNH. And I started off with this XKCD comic. If you don't know xkcd.com, it's a fantastic source of hilarious science and math comics. In this comic, someone is apparently able to see all of the atoms in a piece of material by looking at it. And the other person is just baffled. So before I get started with the science side of my talk, I thought I'd just tell you a little bit about my background, so you know where I came from and what my career has looked like. I grew up in Oregon, starting on the Oregon coast and then moving to Central Oregon for high school. And then I went to college at Occidental College in LA, where I got my bachelor's degree in physics. And then I had this wonderful opportunity to work at the Jet Propulsion Laboratory after my bachelor's degree. And this is a picture of me in a bunny suit working on a temperature enclosure for testing a telescope. So I do have some prior experience in the space world, but I kind of took a different turn after LA. I applied to graduate school and ended up at Brown University in Providence, Rhode Island, where I studied things that were really, really small and really, really cold, and started looking at superconductors, which are materials that conduct electricity with no resistance, and ended up finding out that some of those superconductors can be turned into super insulators, which was super strange. And then I took a postdoc at Ohio State University in Columbus, Ohio, where I worked on spintronics and learned how to use a scanning tunneling microscope, which is what I'm going to tell you about today. And I also started working on these two-dimensional materials when I was a postdoc. And now I have a lab at University of New Hampshire. I'm an assistant professor there, been there since 2015. My group studies these two-dimensional materials by imaging them. And so I'm going to tell you about how those things work today. A two-dimensional material is usually, this is like one atom or one molecule thick material. And we call it a two-dimensional material because the electronics so it does have some thickness because the atom has to be there. But the electronics in that thickness behave as if they're in two dimensions. So it doesn't really make sense to consider the electrons in the material to be three-dimensional. The electrons in the material are really confined to move in two dimensions only. So that's why we call them two-dimensional materials. It wasn't even clear that it was possible to isolate a single layer of atoms or a single molecular layer until around 2000, 2005, something like that, when graphene was discovered. And it wasn't really discovered. We always knew that a single layer of graphite was graphene. However, we didn't know we could isolate it. And we didn't know that it would have such different electronic properties. And graphene, the discovery of graphene and its new properties did win the Nobel Prize, I think, in 2012. And I'm showing this picture here because a 2D material is a crystal, but it's also flexible. It's like a sheet. So it's like an electronic fabric, and we can actually use it and manipulate it. that way. So I'll talk a little bit more about 2D materials toward the end of the talk. But one more thing before I go on is that the other advantage of 2D materials is that you can tailor their surfaces. So if we start off with this material, which is like graphene, but has hydrogens attached to some of the carbon atoms, that's an insulator. It doesn't conduct electricity at all. But if then we went and removed some of the hydrogen atoms, we would get a channel that was metallic, like graphene. So you can, there's just this, there's so much possibility in tuning these materials. You can imagine even whole circuit boards just made of these two-dimensional fabric-like materials. So the plan for this talk is to talk about atoms. What are they really? How do we see them? And then we're going to make an STM. I'll tell you about that when we get there. And then we're going to have a whirlwind tour of an STM experiment, and then talk a little bit more about current research in 2D materials. So when you hear about atoms, you may imagine a picture sort of like this one, where there's a nucleus that's made of protons and neutrons, and then there are electrons whizzing around the outside, which may be even drawn as little balls that go in orbits. Okay, it's a very solar system-like picture, but that's not really a good description of an atom. This is a more accurate drawing, although not perfect. Really, the electron exists in a kind of cloud around the nucleus, and the cloud doesn't tell you where the electron is. The cloud is telling you the probability density, which means where the electron is most likely to be if you were to go and poke it and look for it. So where the cloud is dense, you're more likely to have the electron there. And when the cloud is faint, you're less likely to see the electron there. This is a manifestation of quantum mechanics. This is how electrons work because they're quantum mechanical objects. So even if we look at the simplest atom, these are the wave functions of the hydrogen atom. And the wave function is the probability density of the electron. So these are also often called orbitals. These are the places you're likely to find electrons near the hydrogen atom. And you can see there are many options. So this is just one atom. But as you go, so this is the simplest one. So as you go up in energy, these shapes change. And then if you go along the horizontal direction, you're actually going up in angular momentum. So the electron can be occupying any of these states depending on its momentum and energy. And then that tells you the probability density of where the electron is likely to be. So this is a much more accurate depiction of what an atom is. It's a nucleus, which we don't image at all. It's way, way too small. And then the electron cloud that surrounds it. And the electron cloud isn't really a diffuse electron thing. It's really just telling you the probability density of where the electron could be. So for a sense of scale, if we scaled an atom up so that the atom was the size of your piece of pizza, then your piece of pizza would scale to be larger than the sun. That's how enormous the change in scale is between an atom and your pizza. So in that sense, we are talking kind of astronomical sizes, but the other way. We're talking astronomically small sizes. So things that are this small, how can we image them? Well, let's look at the, this chart is pretty helpful. It tells you what you can see with the different tools. So with your eye, you can see easily things down to maybe the thickness of a hair. And then you need to start using a light microscope. And the light microscope uses the rays of light and optics to enlarge objects, but it's still using visible light that reflects off the objects. And so you can go down to, with a light microscope, to somewhere between the size of a bacterium and the size of a virus particle. But then you're getting to be on the same size as the wavelength of the light. So if you're getting to be the size of the wavelength of the light, then the ray optics you're using to image the object won't work anymore. You're going to have too much diffraction and interference. So then you need to use something that has a smaller wavelength. And for that, we actually use electrons. So electrons can be seen as particles, and they can also be seen as waves. And that's a manifestation of quantum mechanics as well. So if we use an electron microscope, and instead of bouncing light waves off of objects, and we bounce electrons off of objects, then we can image things that are much smaller. So these are often, most of this is referring to what's called a scanning electron microscope. And that is actually shooting a beam of electrons down and then recording what's transmitted or reflected. And for that, you can go down to the size of a glucose molecule. This is a bit questionable down here, although a transmission electron microscope can image atoms, and they do use free electrons in that same way. The microscope that I use also uses electrons, but in a different way. And I'll show you that now. So how does a scanning tunneling microscope work? It's actually pretty simple. It's a wire. It's a cut wire. And you get the wire really close to the sample, and then you move it a very tiny amount so that it scans the surface. And the wire is not actually touching the sample. It is a little distance away. And by a little distance, I mean a nanometer. So like the size of 10 atoms away from the surface. So when it's that close to the surface, if you apply a voltage across between the sample and the tip, so you put like a battery there, then there's some probability that your electrons from your sample will tunnel into your tip. That means they aren't in the sample anymore and they appear in the tip. So this is quantum mechanical tunneling. It's a really cool phenomenon. All we can say about it is the probability of an electron making that tunneling transition. We can't say whether it will definitely happen or not. But if we make an attempt at it many, many times, then statistics are our friend, and we can turn probabilities into numbers. So we can measure a tunneling current of electrons over this gap. And the big difference between this microscope and the electron microscope I showed on the last slide is that those electrons in the scanning electron microscope are free in space, kind of like the rays of light. They're shooting through space. In this type of microscope, the electrons never really exist in this barrier. This is a forbidden area. They can't be here. They can only be in the sample, or they can be in the tip, which is this wire. So the electrons are never in this gap between the tip and the sample. They tunnel through the gap, across the gap, but they never exist in the gap. So this is a really funny phenomenon, quantum tunneling, but it's really cool. And it's especially cool because we use it as a tool to measure surfaces. So quantum tunneling across a nanometer scale gap. The probability that an electron will tunnel depends exponentially on the distance between this last atom on the tip and the first atom on the surface. And that means that we're really sensitive to changes in height. So if the tip is over the top of one of these blue atoms, we will get a bigger signal. And if it's in between the blue atoms, we will get a lower signal. So as we move the tip across the surface, it traces out the contours of the atoms on the surface. And that is the mechanism that we use to image atoms. This is an example of an image we took in our lab at UNH. The purple circles are silicon atoms, and the blue lines and traces are the spaces between the silicon atoms. And this is a really beautiful surface. This is the silicon 111 plane. And this is called the 7x7 reconstruction. It means that at the surface of the material, the atoms rearrange themselves into this really cool pattern. So that in itself is really cool. And this is actually one of the first big mysteries that STM was able to solve, because before the invention of the scanning tunneling microscope, we were only using diffraction to see surfaces, to see atomic surfaces, which is a much more complicated technique, and you don't get real space images. So people didn't know what this special reconstruction was. And when they imaged it with an STM, it was like a revelation. Oh my gosh, this is the pattern we've been seeing in this other tool that we couldn't interpret. Another miracle of the STM that I want to point out is that in order for this to work, you have to be able to move that wire across the image, across the surface of the material, really, really slowly, like 1 angstrom per second across. So this image, every line in this image probably took 10 seconds to scan. So that's how slow some of these images are to take. Now, how do you even control something mechanically on that kind of scale with that kind of precision? That is the property of piezoelectrics. So this is a material. It's represented here by this red tube. It holds the tip wire and it deforms slightly when you apply voltage across it. So you apply like a couple hundred volts across this piezoelectric material and it will bend it. So you're basically bending this tube, and then that drags this tip across the surface. And the way that this image is line by line. You'll see in a second. So it does one line and then it does the next line. Okay, so Mirka, should I pause here for questions? Are there a lot of questions, or should I keep going?
At the moment, we don't have any questions. So I'd say if people are listening the way that I am and thinking like, oh my gosh, now I actually understand what a scanning electron microscope does. And oh my gosh, I didn't know that that's how that worked. Now would be a good time to put some things in there. I don't know if you're going to get to this later, but I was just wondering about how long it takes to do something like this.
Yeah, so I do have a bit
Okay.
bit later that might help with that.
Okay, so I would say, why don't you keep going for a bit and we'll see
Okay.
what questions come in.
Okay. So I'm going to put that last comment off for a second. Here's the larger scale image of this surface. And you can see a lot of really interesting things in here. One thing is that the pattern definitely repeats, like this circular group of atoms is repeating down here. But you can also see a lot of defects and other features in this image. Like here, it looks like there's an atom missing from this spot. And then here, there's just a lot of disorder around this area. So image surfaces aren't perfect either. And sometimes studying those defects is where a lot of interesting physics comes from. Okay, so this is the interlude called Let's Make an STM. So this is an activity I've done before when I've given talks in person, sometimes with candy and pretzels. So I apologize that I cannot hand out candy and pretzels, but hopefully you can still follow along and maybe try it yourselves later. So first you need an atomic surface. So one way to get an atomic surface is to build a little square paper boat and fill it with gumballs. M&Ms, peanut M&Ms work pretty well too, but you want to be able to put enough gumballs or M&Ms in this contained area that you get a pattern on the surface, and you can manipulate your pattern, manipulate your surfaces to have all kinds of different features. So this particular surface is pretty defective, but you can see there's still some periodicity in here. So that's what you would do first, is make your atomic surface. And then this is a video playing of 2 high school students that came to work with my lab a little while ago. And they made these YouTube videos for middle school students on how to make an STM. So this is part of one of their videos that they made. And you can see that she's made this atomic surface and is tracing it with a compass tip. So she traces it by hand with the compass tip, and then on this vertical paper, it makes the trace of the top of the gumball atoms. So you get this bumpy pattern tracing the top of the atoms, and you get to visualize a little bit how the STM images line by line. So in the video, it's only repeating the first line, but in reality, you would want to repeat this as you scan through the atomic crystal from top to bottom. And then you take your lines that you drew on the paper and you project them in 2 dimensions. So here, the bright spots of this surface, which turns out to be graphite, the bright spots would be the tops of atoms, and then the dark spots would be the dips between atoms. So you can take your trace that you made with your pencil and either actually or just visually imagine turning it into a 2-dimensional image. Every line in your image is a trace like this one. And then the color is just added as a map to understand, to be able to see the texture. Okay, so that's the make your own STM. And now I wanted to give you a little bit of a tour of what it's like to do an STM experiment. So these are images from the lab where I did a postdoc, because that's when I took all of these images. So that's why it's not from my lab at UNH, but I'll show you some pictures of that in a little bit. So first of all, the STM is inside this tiny little window tucked away in an ultra high vacuum chamber. So the vacuum in this chamber is better than outer space, actually. And the temperature is pretty low, pretty comparable. This one was at 5 Kelvin. So that's 5 degrees above absolute 0. So your STM is tucked away in this ultra high vacuum, low temperature environment. And it's also hanging from springs to reduce or eliminate vibrations. And if you were to open it up, you can see on the right a more detailed picture of what it looks like. In this part, this is where your sample and your tip are. So the tip is just this wire. It's in this tip holder here. And then this little disc is a copper crystal. And then it's held down by these teeny little springs. These things are small enough that they're hard to manipulate with your hands. And then just for scale, in comparison, this is the size of a penny. So this is a really tiny little thing that we're handling when we put all this together. And this is an example of an image that I took on a copper surface. And so this image is 80 nanometers. This was the biggest image we could take with the microscope at Ohio State. 80 nanometers is still extremely small. And we could take this image all in one go. This image would take about 3 minutes to take, the whole thing. But then if we wanted to go around and find out what the world looked like to the STM, if we wanted to access all of the regions of space that the STM could access and look at the whole sample surface from the perspective of the STM, we would have to take a lot of images. So this is the entire region that the STM can reach after you get your experiment all set up. So this is the world according to the STM. And this copper surface we were studying because we were trying to grow graphene on copper. And these smooth little islands here that I just colored in purple, those are all graphene islands that we grew on this copper crystal. And this whole thing is a little bit bigger than half a micron. And you'll notice that the edges, there's a whole huge gap in the center of this image. And every time that we get close to this empty region, there's a lot of stripy stuff, okay? All of that stripy stuff is a tip sample interaction, meaning that atoms are jumping back and forth from the tip to the sample and messing up the imaging. Now, if too much of that happens, your entire experiment is over and you have to just start new. So we avoid this region whenever we see bad imaging, like the edges of this huge square here. We just move away, keep to the easily navigable areas. And so in ancient times, when people were navigating the oceans, they would write, "Here be dragons," wherever there were seas that were not easily navigable. So there's a corollary at the STM world when you're exploring a new surface. And this was a picture of a dragon that a graduate student I was working with at Ohio State drew. And I just think it's great. And also, if you go there and run into the dragon, you have to start your experiment over. And it is sad and time consuming. Going back to the scale of things for a minute, here's the penny again. This little crystal is a single grain of salt on the penny. And you can see Abraham Lincoln sitting here in the Lincoln Memorial. Okay, so the salt is 300 microns. And here's Abe Lincoln. If Abe Lincoln was carved perfectly into this penny, then the entire map of the world I just showed you would be the width of one of Abe Lincoln's hair in the back of the penny. So that's the size of copper crystal that the STM tip could access. Just a very, very small world. Another way to look at it is if you look at the pixels on this photograph of a penny, you could fit 900 maps of the world in one pixel. So each one of these little white squares would be one map of the world that I just showed you from the previous slide. So very tiny areas. And we weren't even looking at atoms. We were looking at this giant area according to the STM tip. So how much further in do we have to go before we see atoms? So let's take a look at this nice graphene island here. We zoom in a little bit more, we see some noise, but no atoms. We zoom in a little bit more and we see a pattern, but this bright pattern that you see is actually something called a moire pattern. It's the pattern due to overlapping patterns. This isn't the atoms either. Whoops. And finally, if we zoom in more, we can finally see the graphene atoms, which form these rings around this small structure here. So that's how you get from the back of a penny to an atom. Okay, this is another image this image is from our lab at UNH. This is graphene, the same material, but on a different substrate. This substrate is silicon carbide. And silicon carbide is a nice substrate because we can grow graphene directly on it. So silicon carbide is a crystal that's made of silicon and carbon. So you can heat it up and it will preferentially evaporate the silicon so that you're left with layers of carbon by themselves. And the layers of carbon by themselves will reorganize into graphene. So it's a really nice way to grow graphene. Our collaborators did that for a project, and this is an image that resulted from that. Okay, so the other thing I wanted to tell you about STM was that in addition to being able to image atoms, because we're using electrons to probe the surface, we can also image changes in the electronic structure in the surface. And an example is this feature here. It's this beautiful triangular shape. The atoms are in rings, like around this circle right here would be a ring of graphene atoms. So this structure is not an atom. This is not due to atoms. This structure is because there are like electron orbitals hanging out here, and we're imaging the orbitals around the atoms. There are suddenly a lot of states that electrons can tunnel into here, and there are fewer states for electrons to tunnel into over here. So this region turns up really bright. So we have, I guess the summarized way to say that is we have sensitivity to see the electronic states as well as the topographical atomic corrugation. Okay, so on that note, this is another material we've looked at. This material is called black phosphorus. If we were to look at the crystal in 3 dimensions, it has this sort of corrugated cardboard appearance with the layers that are separated by gaps. This image you're seeing is from the top of this crystal. So you flip this crystal over and you see there are these zigzags here. Let me go on this one. There are these zigzag rows of atoms on the top. So that's what we're imaging here, are the zigzag rows of atoms on the top of this black phosphorus material. Now, really interestingly, what happens, like if you take this one atom, for example, and if you took it out of the lattice, sometimes this happens. Sometimes there are missing atoms. It's a defect. In black phosphorus, if you have a missing atom, you get this enormous electronic signature. It's got this big dumbbell shape that spans 20 rows of atoms. And then there's this cool ring that shows up in STM images. And that's sort of a detail of the STM tip interacting with the semiconductor bands in the material, but it still shows the really large electronic effect in this material from just one missing atom. So this is why studying defects can be really important in materials, because if you have one missing atom and you have this big electrostatic cloud from this one missing atom, then if you were to try to use this material for technological application, like for instance, a transistor, you would have a lot of issues with the quality of the material and how easily electrons will move through the material. The mobility of your semiconductor will suffer because of these kinds of effects. So STM can tell you about those local changes to the electronic structure that happen because of defects. So in summary about 2D materials, they're really exciting because they're so tunable, and they're really similar to natural fabrics and a weave, like the weave on the fabrics. So let's see what this fabric is actually made of. If you take cotton and look at what it's made of, it's got all these fibers, and the fibers go down to this really fine biological structure. And then if you zoom in on one of these things, you get finally to the atoms. Okay, so the atoms are all in these larger fibers. But in graphene, here's a TEM image of graphene. So this is transition electron microscope. And all of these folds are also wrinkles, very similar to the cotton photograph, but this entire sheet is just atoms. It's just graphene atoms. So it's really interesting to think about these 2D materials as fabrics and also as tunable surfaces. We can manipulate their properties directly. So finally, I just wanted to give you a little bit of an idea of what is in my lab currently at UNH. This is our ultra high vacuum chamber. Ultra high vacuum is 10 to the minus 10 millibar. So much, much, much less than atmospheric pressure. We have a load lock. So I like to think of these ultra high vacuum chambers as like reverse space systems, like a reverse spaceship, right? So if you were out in outer space and you wanted to get into the spaceship, you would have to go through a load lock where it would first be open to the vacuum of space. Then you would go inside and close it up, and then you would pressurize it. And then you could enter the rest of the spaceship from there. This is like the reverse spaceship, because in order to get things into the vacuum chamber, we have a load lock. Well, we close this valve and then we vent the load lock to atmospheric pressure, open it, put our samples and tips in, and then we close it up and we pump it down to low, very low vacuum. And then we open up this valve here and we have a transfer arm that we can use to push the samples and tips into these other chambers. This chamber is a prep chamber and a probe chamber. We have some tools in here. This is where we can prepare samples and make some things and do a couple measurements. There's another valve here that we can keep shut or open, and we can move things. Oh, the overlay is a little off. We can move things from the prep probe chamber into the low T STM AF, we also, I didn't talk about this, low T STM AFM chamber. So we can put our samples inside this chamber for imaging. Inside this chamber is where the STM lives. These metal cans are really just for the cryogens, because our STM in here is kept at 10 Kelvin. So we need these shields to help keep it cold. But inside of here is where the actual STM is. In our instrument, the wire points up and the sample surface is right above, like this. So you can see here this very sharp wire. This is the surface of graphite. And you can also see the reflection of the tip in the surface. So what we do in practice is we move the tip close to the sample until the reflection and the tip are almost touching. And then we engage an auto approach system that checks for tunneling current every time you get a little teeny closer. And that is it. So thank you very much for your attention. I've left, I think, a good amount of time for questions. I'd be happy to stay and chat as long as people want.
Okay, and we definitely have some questions now. So I
Great.
think some of them are a bit more about the process and some are more, I think, about kind of the larger ideas here. So one question that we had was, the scanner records values that you then assign colors to. Is that how those colors get that way?
Yes, and one of the most fun things my graduate students do is keep changing the colors until it looks pretty. So we have software that you can use to manipulate the color scheme. And sometimes some color schemes are more useful for viewing a surface than others. So it's all false colored.
Yep. Okay. And then kind of going along with what we see in those images, is the lack of atoms in the images a defect or that they have moved?
Both. It could be that they were never there and that's how the crystal grew.
Mm-hmm.
It formed without that atom there. That's possible. It could also be that something knocked it out. And sometimes we knock the atoms out ourselves. You can create defects with the STM tip. So it could be multiple things. And sometimes we do chemistry on the surface, which pulls the atoms off of the surface, so that we've created vacancies that way.
Okay. And so we have a question, what colors are atoms naturally? Is there an answer for that?
That's a really cool question. I guess to answer that question, you have to first think about what colors are at all.
Right.
And colors, as we see them, are different wavelengths of light. And so color, like when you say that your book is red, what it means is that the book is reflecting primarily red to your eyes. So since we're not looking at the atoms with our eyes, I would have to be really creative to think of a way to say what color they are. But I love the question. So I'm going to keep thinking about that and see if I can come up with a better answer. But in the way that we normally see colors, atoms don't have a color.
Okay. Do the atoms always have the same distinctive patterns and landscapes on the same materials?
If it's the same atom in the same crystal structure, it will always look the same, except for whatever defects may be present. If it's a different atom with this, sometimes there are multiple atoms that have the same crystal structure, like gold and copper. The crystal structures are identical, but the atoms are different. They have different numbers of electrons and protons. So the shape of the atom is different. And how we would tell the difference in our instrument would be by looking at the electronic structure of the surface, and not by looking at the pattern of atoms.
Okay.
So I hope that if that question asker would like to add on to that, maybe I can come back to it in case I didn't answer it.
Okay. Now you had mentioned seeing defects, looking for defects, and then that kind of tells us new stuff. What do the defects tell us?
Sometimes the defects can tell you new physics. So, for example, okay, so one project we're working on in my group is understanding how electrons travel through a crystal when you make it more and more and more defective. And if you start out with a really good conductor, but you just keep changing the positions of the atoms or removing atoms to create defects, eventually you're not going to have a good conductor anymore. So by creating defects, we can study the physics from a really good crystal that behaves like a metal to a really bad crystal that behaves more like an insulator. And there's some really fundamental stuff in that phase transition that we try to understand.
Okay. And I feel like some of these are kind of going together. So the same person then said, is your goal to look for perfect material?
No, not my goal. I like defects. In fact, there's one image, when we first installed the microscope and we were looking at a brand new crystal of graphite. It was a really, really good sample. And I was dying to see a defect somewhere, because then I'd have something new to measure. But I couldn't find a defect in the whole thing. It was too perfect. So we took that one out.
Boring.
I mean, it is really cool that crystals can be so perfect. It's a really cool fact of nature, but the defects are more interesting.
Mm-hmm. So I think kind of, tagging along with this, what are the applications of this work? Is this still in the theoretical realm, or are there ways this technology has a practical application?
There are definitely practical applications. It's not something I'm personally going to work on, but my goal is to help everyone understand the fundamentals, so that engineers and materials physicists can use that information to decide which technologies should be developed. For example, the black phosphorus material that I showed, that's a really, really attractive semiconductor. It has really ideal properties for transistors, and we can make it down to a single layer, so much thinner than the existing transistor materials. It's also made out of phosphorus, which is a really abundant material. So this is a really attractive place to think about making new kinds of transistors. But in order to get to that technological advance, we need to understand how the defects affect the properties of the material that would be relevant to the transistor. So that's where I see myself playing a role in the new technologies.
Neat. So there's another question that it feels a bit like a prod to go in a certain direction. Can you tell us about the pink wave?
Oh, that is a inside question
Gotcha.
about my graduate school stylistic choices. There is a pink wave that is published, and I made it bright pink.
Nice.
Yeah.
Very nice. Another question was, did we know that atoms existed before there were electron microscopes to see them with?
We did know that atoms existed. And we knew that, I think, more or less from chemistry. But then we first started seeing direct evidence of atoms when we did scattering experiments with electrons, which are a little bit different than these direct imaging experiments that I'm showing here.
Mm-hmm. Could you ever transfer a pattern of atoms on one material to another without changing its pattern, or is that unavoidable?
That is a totally awesome idea, and one that a ton of people are working on right now. So it's excellent scientific intuition. There's an entire field right now where people are picking up these single layer materials and stacking them on other single layer materials. And that creates all kinds of new things happening. It's really cool. You get, first of all, you can basically treat these things like Legos and make your own crystals just by Lego stacking these crystals. And then the thing that you end up with is not exactly the sum of its parts, because all of the parts are interacting with each other. So you get all kinds of interesting things coming out, and a lot of things that are not easily predictable. So it's leading to new discoveries.
That's very neat. We did have someone who asked what the vacuum pressure was like in space. I don't know if you know that.
It is a number I should know. I don't remember it.
Well, so I thought, well, I'll look this one up myself, because I thought, well, maybe I should know this. And what I found is I found numbers for ultra high vacuum, extremely high vacuum, and outer space.
Okay.
And it's telling me either torr or PA, and I'm not sure which.
How about torr?
Torr. Okay, so for ultra high vacuum, it says 1 × 10 to the -9 to 1 × 10 to the -12.
That's what our chambers are.
That's what your chamber is. Okay.
Mm-hmm.
For extremely high vacuum, it's less than 1 × 10 to the -12. So, more of a vacuum. And then outer space apparently can range from 1 × 10 to the -6 to less than 1 × 10 to the -17.
Ooh, okay.
Yeah, that's pretty crazy. That's a tiny, 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 tiny number.
That is crazy.
Goodness.
There's not very much out there in space.
Right. Exactly. So I hope we kind of answered that question. I mean, it's a range, obviously.
Thank you for looking that up.
Yeah, well, I was like, I feel like as the representative of the Space Museum, I should help with that one. We had another question, which is, how do you get the tips so close? I mean, you mentioned kind of looking to see where it starts to mirror, and then using kind of a program to kind of check. Is that a timely process? Does it take a while to get to that right spot?
It depends on how gutsy you are. If you get the mirror image really close to the tip, then it'll be a lot faster. If you want to play it safe, because if you crash the tip into the surface, you kind of have to start over.
Right.
You make a big mess. So you don't want to do that. That's a big waste of time. So depending on the level of comfort you have with it, if you start with it about a pinky finger away on the screen, then it'll usually approach in less than a half an hour. But you do have to wait. And it's kind of like a video game. It's like an inchworm. It just jumps, it goes up one step, and then it pushes itself forward, says, is there a tunneling current? Nope. Okay, pulling myself back, take another step, check again.
Wow.
So it's a little program that auto approaches for us.
So we had more of a kind of just general question, which was, what inspired you to study condensed matter physics specifically?
That's a really, really fun question, because I really thought I was going to do astrophysics. And then I would be giving quite a different talk. So when I started graduate school, I was like, I don't know. I worked with a condensed matter physics professor when I was an undergrad. I'm not sure if that's the direction I really want to go. Astrophysics seems so much more interesting. But then I learned about the different groups that were hiring students at Brown, and I just fell in love with condensed matter. I mean, part of what I loved about it was that you have the sort of high level physics stuff, like what are these states in this material? How can we control them? What does it say? How do these electrons interact with each other? You have all of these big physics questions. But then you have this data analysis where you're working with your data and you're trying to understand it. And that's all working on a computer for the most part, and trying to understand the literature. So there's this analysis piece. But then the piece that really drew me to condensed matter was working in the lab, building things, working with my hands. And condensed matter is one of the research areas where each lab does their own work for the most part. There are a lot of collaborations, but if you want to do an experiment, you have all of the tools in hand to make it happen. Like you can work in your own space and use your own resources to do something. So, and that suited me because I like to fiddle with things and see if I could make something work better and understand instruments. And so that aspect of it really drew me to condensed matter.
Neat. I think, for some people, being able to get their hands on something can really be engaging. We have another question. Why did scientists choose to use a wire for the point? Could you have used anything else instead?
Mostly because wires are really easy to handle. So people have used other things. For example, a very fancy kind of tip is one that has a carbon nanotube sticking off the end. Really hard to make that work. So a wire is much more forgivable. And because the metals are really ductile, when you just take this piece of wire and some basic like Home Depot wire clippers and you go whoosh, and it leaves almost always a really nice fine point on the tip. And almost always there's one atom that sticks out just a little bit further than all the others, so that your tunneling junction is from one atom on the tip to your atoms on the surface. So metals just work really well for that.
Neat. I just also love the idea that this is almost like a low-tech answer.
It really is.
It.
I mean, I didn't even tell you about the Scotch tape, but that's the other basic tool in my lab.
Fantastic. Another question regarding the electron activity image you showed with the pretty purple and yellow. Do we know why electron activity surges in some areas but not others?
Yes, I think I know what you're talking about. I think it's, sorry, going back, this one. So this is one of those things that you can't look at directly and understand. This is definitely an electronic effect. Like I knew that when I took this image. And it's definitely related to some kind of defect that's probably in the center of this shape, in the center of this pattern. But in order to figure out what it is, since you're imaging a combination of the electronic effect and the positions of the atoms, you have to use simulation tools to try and help you understand this kind of image. So what people have done to understand this defect and others like it is they use basic tools, like basic equations for physics, and something called density functional theory to simulate images. And then from the simulation, you can piece together what this thing is. Like, for example, if it's due to a missing atom, then you will be able to see that if you pull this atom out of this lattice and then simulate an STM image, the bright spots here are due to electrons in the D band or something like that. So I'm not sure that's a very direct answer, but this I don't remember what for this specific defect, what the topographical reason is for it. But what we're seeing in the yellow is primarily an electronic signature of the orbitals that are left behind from the defect.
And then I think this must be another inside question. Nev was wondering if you could image a piece of wood for her in the lab.
Neve, my neighbor. Wood is a very bad sample for STM because we rely on the electrons being able to move in the samples. So we can image metals and we can image semiconductors, but wood is an insulator. So I really wouldn't like to put that in my microscope. So if you find me some kind of, if you find me some natural graphite, I'll put that in my microscope.
And then I had a question. You mentioned at the beginning that we think of this as a 2D material because it's really just like you've got the atoms there, but you're really not thinking about kind of the space above and below for the electrons. You're really thinking about kind of the movement in between. Does having just that single layer of atoms, does that change the motion of the electrons themselves?
Definitely. So the great example of that is graphite and graphene. Graphite is the stuff that's in your pencils. We've been using it for hundreds of years because it sloughs off because the layers come apart so easily. But when you look at the electronic structure of graphite, it's really boring. It's a pretty bad metal. It's a semi-metal. It doesn't conduct really great. It doesn't have any special properties. It doesn't have a semiconducting gap. So it's just kind of a boring electronic material. But when one sheet of graphene was taken out of graphite and measured, it had all kinds of interesting electronic properties because you've changed the wave function. The thing that supports the electrons, the quantum mechanical object, now has different environment above and below it. So we call those boundary conditions in physics. So when you change the boundary conditions, the entire solution to the problem changes. If anyone's done differential equations, that's a familiar idea from differential equations. If you change the boundary conditions, the solution is different. So the same thing applies here. If you change the boundary conditions, all of a sudden the solution to the electron problem is different. So you get a completely different electronic structure. It's really unique. It's got linear band structure. You can simulate relativistic things with it. It's pretty cool. Didn't have time to talk about it here.
So Ben is asking, and I think this may be about the graphite that you just mentioned, is there a way to image the layers below the surface?
Sometimes we see things on the second or third level. So sometimes you can see defects, like if their electronic signature goes through the layers, then you can see the defects that are in layers below the surface. But we won't image the atoms in the layers that are below the surface because our sensitivity is really to the surface of the atoms itself.
Gotcha. Okay, and then David said, thank you very much for exposing me to such cool stuff. I agree. I feel like I've first of all understood things about science classes that I've taken and microscopes that we've used and that no one ever took the time to explain. So that right there is fantastic.
You probably have a lot of telescope experts, but maybe not so many microscope experts.
But also just to kind of really have a better sense of how you do this and what it means, because it is so hard for me to conceptualize, working on that scale. You talked about, astronomically small. I have just as much trouble understanding the size of the universe as I do like the size of this. And
yeah, so it's pretty amazing because we handle this stuff every day. It's everywhere we look.
It's phenomenal. So I want to give everybody another moment or two. If there are any other questions or comments that you want to put into the chat, please do. If you're the kind of person like me who thinks about stuff later on and then says, I wish I'd asked that question, tomorrow you'll all get a message from me thanking you for being here, asking if you have any suggestions or comments or things like that, and it'll have my email. So you can definitely send me any questions, any lingering ideas, and I will be happy to pass them along. to Dr. Hollen so that she can respond as well. So,
and feel free to reach out to me directly too. I'd be happy to get emails. You can find me on UNH's website pretty easily.
indeed, all you have to do is Google Shawna Hollen at UNH, and she pops up right there, which is fantastic. And Emily said, great job taking a complex subject and making it understandable to non-physicists. I completely agree, because I felt like this felt very outside of my comfort range. And now I'm like, oh, I do actually understand what you're doing and how you're doing it. And I have a better sense of the process. So thank you so much. This was wonderful. Okay, and I want to thank everyone else who joined us. I learned a huge amount. I hope that you did as well. We'll keep doing these online Superstellar Fridays while it makes sense. And at some point, I hope to see you all in person again. But it's wonderful that we can spend some time together this way. So I hope that you all have a wonderful weekend. And I'm going to simply end the webinar so that there's no confusion about whether or not it's done or not. So good night, everyone.